We want to look now at some specific applications of a geometric progression. And the first one is what we basically are doing with superannuation. The superannuation is often called annuities as well. So it's a special word, annuities. And that's what it is. And you see that word's coming up in superannuation. Now, if you don't know what superannuation is, basically every time you get paid in Australia, you have to your employer makes a contribution to a fund, and the idea is that that money goes into a fund and it starts to earn interest, and that stays there for a number of years until you retire, and then you can take that money out. So what it's doing though is accumulating interest. All these questions are based around that. They're not as complex as a real superannuation situation, but it's the idea of getting a regular interest rate for a certain amount of time, but making that regular payment. So what these questions basically come down to is a sum of a lot of compound interest questions, and those, fortunately for in these problems, they form nice patterns. And what we want to do is find that pattern, look at what the geometric progression comes out as, and then we're able to find the total amount that's earned by regular contributions over time. And it is closely related to compound interest. Let's have a look at the first one. It's got Susan was born, and her father's depositing $130 in a trust account. It gains 12% per annum, and it's compounded annually. And then he decides to deposit $130 in the account each time Susan has a birthday, up until her 17th birthday. So, firstly, what we've got to look at and go, well, how many times does he make deposits, and how long is it in there? So, the first part of the question is really just compound interest, because it says show that the first 130 comes to that amount on her 18th birthday. So, if it's deposited when she's born, then after 1 year, when she turns one, so the amount's been in there for a year. So once she's turned 18, the amount's been in there for 18 years. 12%'s been the interest rate. So the 130's gained 12% upon 12% upon 12% upon 12% for 18 years. And that $130, because of that nice interest rate and being compounded so many times, comes out to nearly $1,000, $999.70. So part two wants us to see, well, what happens if he does that every year? So at her first birthday, he's going to deposit $130, but that's only going to get interest for 17 years, and the amount that he puts in for her for second birthday is only going to get 16 years interest on it. For a third birthday, and so on, up until the 17th birthday, where it's only going to get 1 year's interest on it. So if we have a look at what the pattern is, there after the first year, he puts in $130 and gains 12% interest. So that's the compound interest formula with 1 year there. Don't calculate it out, because we want to do the total amount, so we don't need to see it. We rather in this form at the moment. So after 2 years, at the start of the second year, start of the second year of Susan's life, he puts in $130 for the first when she's born, and then there's that $130 he puts in at the start of her second year, her first birthday. All that amount now is being invested for a year at 12% per annum, and we come up with this pattern. So if we expand it out, so the first amount has had 2 years of interest, the second amount's had 1 year of interest. After 3 years, so on her second birthday, he puts in another 130. So you've got the original amount that was there after 2 years, and then start of the 3 years, he puts in 130, and then for that year, it's calculated interest. We expand it out, so there's our initial 130. That's the 130 from her first birthday, and that's the 130 from her second birthday. So you can see that that keeps going up to 18 years. So after 18 years, we've got this amount. That's the 130 that was put in at her 17th birthday. That one's the one that was 16th, because it's only had 2 years of interest. Now, if you have a look, you can see that's a nice little pattern occurring. Makes it a little bit nicer if we rearrange it. So if we just swap the terms around, well, it's all addition, it's okay. And then we factorise 130 out of it. Again, now we're just making that pattern a little, much simpler. So 1.12, 1.12 all squared. Now what we're going to see is this is a geometric progression. You got a first term of 1.12, common ratio of 1.12, and we've got 18 turns because it's been 18 turns being put in, 18 amounts of investment put in. So there's our data. We can apply the sum of a geometric progression. So the we got 130 outside of a outside of r to the power of n minus 1 all over r minus 1. We can put that straight in our calculator. And at the end of 18 years, putting $130 in each at the start of each year, Susan now has $8,117.16. So be really careful. Set up the pattern every time. I'll say that all the time. Set up the pattern. Don't use a formula. Okay, some texts will use a formula and say, oh, you can just use a formula. If you look at the HSC markers comments, they will always say, don't use a formula. Students who use formulas get into trouble because that, as you'll see in the next line of questions, you start to get little subtleties in the question that you just can't use a formula. So be really careful. We'll explain those as we go along. But take note of the pattern. Set up the pattern each time. Be careful with your calculator with this because it's a really complex calculation.